Hey, hello everybody. I did promise myself and you all that I would start not on Berkeley time, but 5 minutes past, given that people don't have to commute far anymore. So let's get started. Um, I did want to talk about lower bounds, but before we talk about that, I want to present one more thing that's sort of related to counting, um, another algorithm, and then we'll start talking about lower bounds. so So the next maybe so this lecture and the following lecture, one is quantiles. This is also known as like approximate rank and select. And then I want to talk about lower bounds. And when we talk about lower bounds, we'll talk about we'll do it for both quantiles as well as distinct elements. And you'll see some commonality in the in the techniques that we use. And lower bounds are gonna actually, recur actually throughout the semester. So this will be the first introduction to them, but we'll keep talking about ways of proving them. So let's start off with quantiles. So what's the setup? Okay, so we see a stream of comparable items. Oh, actually, I have two Wi-Fi networks and I forgot to put my iPad on the more stable one. Just give me 1 second while I fix that. Okay. Good, we're back. Okay, so this should be stable. So we're going to talk about quantiles first. So we have a stream of comparable items. You can think that they're integers from some universe 1 to u, or you can think they're strings or whatever other comparables. And we want to know what we want to answer, the following kinds of queries. Let's say rank of x. And let's say we see a stream of n comparable items. N is the length of the stream. What is the rank of x in the sorted order of all the stream items seen? So for example, if our stream, our stream, of course, might not come in sorted order. So our stream looks like, we see 3, then we see 3 again, then we see 5, 1, 17, 4, right? And then now, imagine sorting it. Of course, we're trying to use low memory here, so we don't have room to store the whole sorted order. But sorted, this would look like 1, 3, 3, 4, 5, 17. And then if someone says, they want to query rank of let's say 6, the question is, if 6 were in this list, what would the sorted order of it be? And the answer is, well, it would be right here, which is position number 1, 2, 3, 4, 5. Well, okay, so it's also 6. Okay, if someone queried rank, let's say of 18, then I guess we would say that should be 8, right? 1, 2, 3, 4, 5, no, 7. Right? 18 would be here, that's position 8. Position 7. Okay, so that's rank. And select here takes as input some integer n between 1 and n, some integer r between 1 and n, and returns an element of rank R in the sorted order. Okay. Now, as you might imagine, these problems are hard. So we're selling for some approximate version if we want to get away with low memory. Hard in the sense of, in terms of the memory consumption, it's hard to get something that's linear memory. So the way we're going to settle for an approximation is as follows. For rank, we're going to be willing to return the rank of X plus or minus an additive error term of epsilon times n. Okay. Epsilon is some parameter that's given up front before the stream starts. And similarly for select, it's going to return an element of rank R plus or minus epsilon n. So the element that's returned is not necessarily going to have rank exactly R, just rank approximately R in this additive sense. Okay. Notice that we're not returning an approximation of the value of the number at rank. Let's say they're numbers. We're not returning an approximation of the number that has that rank. We're just returning something that approximately has that rank. Okay. So for example, if the stream looked like 1, 2, 3, and then a billion, right? A billion here has rank 4, right? But I'm allowed to return, even in the non-approximate version, if someone says select 4, I am allowed to return 4 or 5 or 6, or basically anything that would have rank 4 in the sorted order. It doesn't have to be close to the number a billion. Okay. So we're just trying to approximate the rank, not the actual number that has that rank in the stream, if that makes sense.
So if you return 4 in this case, would that be like correct?
That would be exactly correct.
Okay.
Yeah. That would not be an approximate answer. That would be an exactly correct answer.
And then for the bounds, it would be inclusive of the endpoints, including 3 and the billion, to be correct?
Sorry, say it one more time.
Yeah, for the bounds, could returning anywhere from including 3 to including a billion be correct?
Oh, like if you returned 3, that would also be exactly correct. Yeah.
Okay, so and then returning a billion would be correct too?
Yes, that would be correct.
Okay.
Anything between 3 and a billion would be exactly correct. Okay. So there's been a lot of. Yeah?
Could you restate the error condition for rank?
Yeah. So X has some true rank in the sorted order. I mean, okay, so it might be.
So plus or minus epsilon n is added to the rank of whatever.
That's right. That's right. And like in this example, there are multiple items that have the same value 3. So it's correct, even in the exact even in the exact problem, it's correct to say that the rank of 3 is either 2 or 3 because it's both the second smallest and the third smallest. Either of those is an acceptable answer.
Right, and rank needs to be returned the correct thing, not just on elements that have appeared in the stream, but on other elements as well.
That's right. The query X here need not be something that appeared in the stream.
Got it.
Okay.
Sorry, Jelani.
Yeah.
So if you get like 10 3s and then a 5, for example.
Okay.
And you ask for the rank of 5, it would be 11, right?
It'd be 11. That's right.
Okay. And if you ask for the rank of 3, it could be anything between
1 and 10 would be a perfectly exact answer.
Okay.
Okay, good. So there's been a lot of work on this problem, and this is actually, I would say, one of the streaming problems that is for which algorithms are widely used in practice. Okay, distinct elements is another one. There's this algorithm hyperlog that is used all over the place in industry. Algorithms for quantiles are similar. In fact, if I share my screen. Yeah, so if you go to this is kind of one of the very popular open source library for the implementation of various sketching algorithms. And one of the things that they implemented is a version of the KLL sketch. It's actually a very new algorithm. It's from 2016. It's a randomized sketching algorithm for the quantiles problem that uses O of 1 over epsilon words of memory for the problem that I told you just now on the whiteboard. And actually, the dependence on the failure probability is also very good. It's log 1 over delta. So 1 over epsilon log 1 over delta. Although the version that they implemented uses a little more space in the theory sense, in the big O sense, but getting the exact optimal right space in big O notation leads to some impracticalities, which you'll get a sense of why as we go throughout lecture and I explain how these algorithms work. So let's go back to the web here. Okay, so there's a natural lower bound for, let's say, comparison-based algorithms. Yeah. Comparison-based, what does it mean? It means that what you're storing in your memory is a subset. Actually, I'll use a definition that is from a paper of Cormode and Viselli actually this year. Essentially what it means is you're storing a subset of the items that you saw, okay? And whenever you see another item, you're allowed to do equality tests with things in memory and also comparisons. And, you know, based on that, you're allowed to store, I think, some auxiliary metadata, like, you know, the result, you're allowed to even store the results of all comparisons you've seen for free. But at the end, you're only allowed to store, you know, so you have basically two parts to your memory. One part is storing a subset of items, K items, okay, where K is like your memory footprint. And the other part of your memory is allowed to store the results of comparisons with things you've seen before in the stream, comparisons and equality tests, okay. And they said that, you know, even in this model where that other part of your memory is allowed to store quite a lot of stuff, that you still have a lower bound where K, just the number of items you store, has to be at least 1 over epsilon. Okay. So a lower bound, oops. Kind of 1 over epsilon words for any deterministic comparison-based algorithm. Right, and also in this model, whenever you answer a query, what you're allowed to do is you're allowed to compare the query item to all the items in the stream, or to all the items that you're storing, these K items, and you're also allowed to look at the metadata. But I mean, essentially, the lower bound is somewhat trivial, and why does it come? It comes because imagine you take the K items that you're storing, let's say you're storing Z1, Z2, up to ZK, and you're storing them in an arbitrary, you're storing them in, let's say this is the sorted order of those items. Right, so if you're not storing, so basically the point is, there are n items you saw in the stream, you're only storing K. So in the sorted order, and as a hard instance, we're only gonna give items that in the stream that are different. We're never gonna give duplicate items. Okay. Which means, you know, all the items that are missing here that you didn't store, there's some Zi and Zi plus 1, where the gap between them has size, you know, this gap has size at least n over K, right? So if you have a deterministic algorithm, then if the only thing that it's allowed to do to answer queries is do comparisons, then any item that it's queried that's in this range is going to have the same exact answer because all the comparisons to the items you're storing are the same, right? And if this gap is too big, then you know that you're not allowed to give the same answer to everything in that range. In particular, if the gap, let's say the gap is bigger than, you know, well, actually, if the gap is bigger than, say, epsilon times n, right, then that means that the thing that's immediately after Zi that you saw in the stream versus the thing that's immediately before Zi plus 1 in the stream are getting the same answer. But these things are more than epsilon and apart from each other. Okay, so therefore one of the answers is wrong. It's not an additive epsilon n approximation. So this basically implies, so yeah, the gap, I want to say the gap is bigger than epsilon n unless k is bigger than 1 over epsilon. Right, so this is a lower bound for comparison-based algorithms. Okay. Kind of more recently, actually, this paper is just from this year. There's a paper by Cormode and Vasselli, more stated. Okay, you can go read it. It's a 20-page paper. I'm not going to cover it in the course. But they show that actually there's a lower bound of omega 1 over epsilon log of epsilon n words for comparison-based algorithms. And this, by the way, is optimal. There was an algorithm from 2001 which actually achieved this bound. So they got the actual type bound for deterministic algorithms that are comparison-based. Okay. And there are algorithms, as we'll see today, which are neither comparison-based nor deterministic. So, it's not, that's not to say you can't beat this bound, but to beat this bound, you cannot be both deterministic and comparison-based. So let's see first some deterministic algorithms for this problem. Okay. The optimal algorithm is due to Greenwald and Khanna. In 2001, and as I mentioned, it achieves the same bound in Cormode and Vasselli's lower bound, 1 over epsilon times log of epsilon n words. I had this plan of covering this algorithm today, but as I was, unfortunately, as I was, reviewing the algorithm details more, I realized it's quite complicated. There are a lot of just details that it would take probably on the order of 2 lectures just to cover this algorithm in full. So I'm not going to cover this algorithm, but I will cover algorithms that do decently. Like, for example, instead of log epsilon n, log squared of epsilon n, 1 over epsilon log squared of epsilon n. And kind of actually an open problem that was posed by Cormode, if anyone's looking for project ideas, come up with a simpler optimal algorithm. So we already know the optimal bound. It's just that unfortunately it's kind of complicated to get it. The algorithm is actually not too complicated. Maybe at the end of lecture, if I have time, I'll try to tell you what the algorithm is. It's just that it's a funny algorithm where when you see the algorithm, just by construction, the algorithm is like obviously correct. What's tricky is bounding the memory consumption of the algorithm. It's not at all obvious from seeing the algorithm that it is low memory. It wants to store basically the whole stream, but it has some pruning procedure that it does periodically to trim down what it's storing. And that pruning procedure is designed in such a way that you guarantee correctness. But if you want to prove that you're using low memory, you have to prove that no matter what the stream looks like, the prune operation will cut out a lot of stuff. And that's the part that's not so obvious as to why that's true. So I will show you two deterministic algorithms today. One is called the Q-digest algorithm. And this algorithm is from 2004. This is due to Srivastava. Let me not say this name because I'm probably going to say it wrong. Agrawal and Suri. And this actually is not a comparison-based algorithm. It assumes that the stream values are integers between 1 and u. U is the universe size. Oh, and I meant to say when we started off, I showed you this this web page from Data Sketches that they implemented quantiles. Why is quantiles so useful in practice? I think a lot of the applications of quantiles in the real world are, you can imagine you built some system and you want to understand its performance, at the tails. I want to say, like, 99.9% of the queries that are made to my system are served within 100 milliseconds, right? So that's exactly quantiles. That's quantiles at the ends, right? Where basically I'm asking about R being, I want to make sure that kind of the vast majority of users don't have a bad experience. It's the chance that you'll have a bad experience using my system is like 0.1%, or maybe even less. So basically I have this stream of people making queries to my system. I can see how long it takes for my system to process the query and spit out an answer. And basically these response times are coming now in a streaming fashion. And then whoever is analyzing my system, maybe the person who built it, who's doing some performance tests, wants to make sure that the 99.9 percentile response time is not too slow, right? So you see a lot of kind of applications in industry that are of that flavor, which is why it's a popular data structure. But let's get back. Yeah.
Sorry, yeah. Can you beat this lower bound in practice if all you care about are rank queries at those tails?
Toward the tails. So actually, there's some recent research, as recent as this year, on instead of additive error quantiles, what they call relative error quantiles. Basically, I don't want the rank error up to additive epsilon n. So I want it instead up to additive epsilon r, where r is the rank that's being queried. And as I said it, R was very large, right? R was almost n. It was 0.999 n. But that's basically, R very large is equivalent to R very small, because you could just use the reverse comparator, right?
Yeah.
The reverse sort. So basically, that what I'm saying is I want my errors to be much better when I'm querying things at the tails. And in fact, there are data structures, even new ones, that can do something in that space, but they're probably not optimal. So getting an optimal such data structure is an open problem.
Cool, thanks.
Yeah. Okay. So the Q digest, this is one that's not comparison based. Greenwald Connaught is comparison based. This is not comparison based. It assumes that the values that I'm seeing in the stream are integers between 1 and u. And I'll explain this algorithm, and then I'll explain one more that is comparison based. And then I'll tell you about randomized algorithms, and then we can talk a little bit about lower bounds for quantiles, and then for distinct elements if we have time, or maybe that will carry into Monday. Okay, so this is a very simple data structure. How does it work? It is deterministic. The idea is you build a perfect binary tree over the universe. So let me try to do that here. So this corresponds to universe element 1, 2, 3, up to u. Okay. And now as I said, there's a tree that you're building over this. Etc. And there's some root up here. So this is a tree of height log u. Okay. And what I'd like to do is I'd like to just store, for every node in here, I'd like to store a counter. And that counter is, it corresponds to, how many elements have I seen in that range of the universe space. So, right, so for example, this node right here corresponds to the range from 1 to 2. But I'm not going to store an item in multiple places. I'm not going to count an item in multiple places. An item is only going to be counted by one node. Okay. Ideally, I'd like to count it at the leaves, but sometimes, I can't afford to store counters for every leaf because that would be U counters. It's too much memory. So at some point, for some items, I'm going to choose to instead store them at higher levels, and I'll do it in such a way that the number of nodes that I need to keep track of at any given time is small. Okay. And I'm only going to keep track in memory of the non-zero counters. And I'm going to basically do this in such a way that I can prove to you that the number of non-zero counters will be small. So basically, so the picture you should have in mind is, let's say I see in the stream 1, 1, 3, 1, 1. Then what the picture should look like is 3 will have a 1 in it. 1 will have a 4 in it because I saw it 4 times. And then all the others will have zeros in it. But of course, as I have longer streams that have more distinct items in them, a lot of the counters are going to start becoming non-zero. I can't afford to store so many non-zero counters. What do I do? So I'll have a rule for myself. Okay. So first of all, I'm going to say that, CX is the counter that corresponds to node X. And then let's say P of X is the parent of X. And this S of X is the sibling. Everyone has a sibling except for the root. Okay. So what's the rule? The rule is going to be that if the counter of X plus the counter of the parent of X plus the counter of the sibling of X, if that's at most epsilon n over log base 2 of u, then I'll set the counter X to 0. I'll set the counter of the sibling of X. Well, actually, I should do it in the reverse. I should do it in the other order, shouldn't I? If I want it to be valid, to be actually correct. Basically, I'm just going to add the children to the parent. That's what I'm going to do. So I'm going to say that the counter of the parent gets incremented by the counter of X and the counter of its sibling. And then I'm going to set the counter of X to 0. And I'm going to set the counter of the sibling of X to 0. Okay. So this is what I mean by items will only ever be kept track of in one node, because originally in the beginning, whenever I see a node in the stream, or whenever I see an element in the stream, it's going to be kept track of in the corresponding leaf. But eventually it might leave the leaf and get merged up into the parent. And then maybe eventually the parent itself and its sibling will get merged into its parent, etc. Okay. Actually, not eventually, but right away. Okay. It'll get right away moved up actually to the...
One quick question for this
Yeah.
plus equals. Why is it a plus equals instead of just an assign? Is there a case where the parent is non-empty and then we can kind of do this like push up step multiple times?
Where the parent is not, well...
Or, because I'm thinking like once you like go to the parent once, we'll never go to those children again.
Once you go to the parent, well, at some point though, the parent can become full, right?
Oh, and then it'll like go up, and then you can do like the leaf nodes again.
Yeah, actually, give me just 1 second.
Of course.
Wait, sorry, can you ask your question one more time?
Yeah. So I'm saying like, okay, so I'm actually, okay, we put our values in the leaf nodes,
Yep.
and then after they get so big, they go up to the parent node.
Yeah, so I guess I shouldn't have said so big, right? It's the
They immediately go up.
yeah, they immediately go up, right? Because
Okay.
you basically apply the rule whenever you can,
Mm-hmm.
right? So the point is, in the beginning, everything is small, right? So everything is 0 in the very beginning of the stream.
Mm-hmm.
So you're basically immediately everything will just get pushed up to the root.
Oh, okay.
Right. But at some, you can think later in the stream. The only reason that I'm not, basically things start getting full from the top down, if that makes sense.
Oh, gotcha. Okay, I had the different image in my mind.
Yeah, things get, yeah. So basically, the root gets full, then some of its children might start getting full, then some of its children might start getting full, etc. Does that make sense?
Yep.
Okay. Okay. So so basically, just apply this rule whenever you can. That's the algorithm. Okay. So now the claim. Oops, what happened to my pen? Claim 1. Number of, let's say, nodes x with non-zero counter is at most 3 log u over epsilon. And remember, we're only going to store the ones that have a non-zero counter, right? And so basically for each node that we store, we're going to remember the counter value as well as like which node it is in the tree. So the proof of this is, if we sum over all u such that c of u is not 0, of c of u plus c of sibling of u plus c of the parent of u, and other than the root. What can we, because the root doesn't have a sibling or a parent, what can we say? We can say that this is bigger than epsilon n over log u times k, where here by, k is basically the number of such u. On the other hand, we know that what is the sum of cu over all u in the tree? That's n, right? Right, because each element is kept track of in some node. Each node in the stream contributes to the count of exactly one node in the tree. Initially the leaf, but it might get pushed up higher in the tree. Okay, so we know that the sum over all u of cu is n. And in this sum that we have here, each node u appears at most 3 times because, it's u once, right? It's u at most once. It's a sibling to exactly one node in the tree, and it's the parent to exactly one node in the tree, or at most one, right? So for some, it's 0 if it's a leaf. So this here is at most 3n. So you just move this around. This implies that k is at most 3 log u over epsilon. Okay. So this says that we're not storing that much stuff. And then, why does rank have error epsilon n? This is also, okay, so the next claim is that rank of x has error at most epsilon n. And that's also quite simple. Just, look at the tree. So here's the tree. We have some query R. Maybe this is R. So just look at the leaf to root path of R. Okay. Just thinking about the ideal picture. The ideal picture is that like nothing ever got moved to the parents. We just have all the information in the leaves. If all the counters were just in the leaves, we would know the rank of R exactly, right? It would just be the sum of all the guys here. Okay. The problem is that some stuff got pushed up the tree, and in particular, it got pushed up to some of the ancestors of R. So now there's some, maybe, from here, there's some mass in this counter. There's also some stuff in this counter. There's also some stuff in this counter that came from things. Some of them might have come from things less than R. Some of them might have came from things bigger than R, right? In particular here, there's some mass that could come from things bigger than R. So basically the problem is in all the counters that are above R, there are all these items that are being counted, and we don't necessarily know, are they less than R? Are they less than the query? Oh, sorry, this is X, not R. X. We're querying X for its rank. So all these things in the root to leaf path, all these other counters, we don't know. The items, the stream items that contributed to those counters, were they less than X or were they bigger than X, right? So they basically contribute to the error. And each counter, you know, how many items does it have participating in it? At most epsilon n over log u. So the total error is the sum over v in the root to leaf, let's say, to leaf path of X of the counter v, which is at most epsilon n over log u times there are log u such v's. So this is at most epsilon n. Okay, so that's it. So this is a very simple data structure. And I'll keep sprinkling open problems. Open, prove in omega 1 over epsilon log u lower bound. Notice this is in words, right? Or come up with a better algorithm. So, you know, we don't actually know an algorithm that's better. In the model where you actually know that the stream elements are integers from 1 to u, we don't have an algorithm, a deterministic algorithm that's better than QDigest. And it's been now, what, 16 years. And we don't have a lower bound showing that this is the best you can do. Okay, so that's QDigest. Now let me give you another algorithm that actually is comparison based. Any questions about QDigest? So algorithm 2, and this is due to Monku, Rajagopalan, and Lindsay in 98. Okay. We're going to get space, which is, so this is, I should write deterministic and comparison based. Deterministic, comparison based. And the memory usage is 1 over epsilon times log squared of epsilon n words of memory. Okay. So what's the idea of this algorithm? It uses something that actually is used in the optimal randomized algorithm as well, which is the notion of a compactor. And it uses a chain of compactors, and I'll describe what this means shortly. Okay, so here it has log base 2 of n over k compactors. And the number of compactors here, I mean, the size of a compactor is k. A compactor just stores a subset of items. So it will store up to k items. And here's the idea. So let's also give these also numbers, which is, let's say this is compactor number 0, 1, 2, up to log of n over k minus 1. When you see an item in the stream, what do? You put it in compactor 0. So compactor 0 will slowly start to fill up. And then now it's full, okay? So what do? You sort these items, and then you promote, let's say, every other item to the next compactor. So all the items at odd indices, let's say. So this is full. Now you sort them, you send every other item to the next compactor. So the next compactor now becomes half full. Okay. And then you empty out this compactor. So this is empty again. It's ready to receive items. And then it's going to slowly fill up again. And then now it empties out into the next compactor again. So now it goes here. Now this compactor is full. So then it promotes every other, it sorts itself. And then it promotes every other item into the next compactor as well. So now this compactor becomes half full. etc. And then this gets emptied out, and this also gets emptied out. Okay. So that's it. That's what you store. Okay. And then I have to tell you how do you answer queries, and how do I set k to get error epsilon, and basically that's gonna give us the bound that I told you. So what is the space bound here, by the way? The space, of course, is I guess k times log of n over k, right? And as you I guess can probably guess, we will set eventually k to be O of 1 over epsilon log of epsilon n. And that's going to lead to the space bound. Okay. So, how do you answer queries, and how do you analyze the error? Okay. So answering queries. Okay, so the picture you should have in mind is the following. So let's say that the stream has the following, sorted order. Of course, it didn't come sorted, but let's just say that this is what the items look like if they are sorted. And then we have some query X, and we want to know its rank. Okay. Now, some of the, not all these items that are less than it are actually being stored in the compactors. Some of them got tossed out because we only promoted every other element. So let's box the elements that we're actually storing. So maybe we're storing this one, and we're also storing maybe that one and that one. Okay. Now, these items are living in different compactors, right? Some are living in compactor 0, compactor 1, compactor 2. What does it mean that it's living in compactor 1, let's say, not compactor 0? Compactor 1, what are those items? Remember, we had in compactor 1, we had our k items. Let's say k is 6 right now. And we only promoted every other item, right? I can basically imagine that what this really means is we basically are like merging these two items as one item. So like this item that is boxed is like the representative for both items. Does that make sense? But we're only going to store the representatives. Okay. So if you want to think about it, you can think that there are these other items that kind of live inside the representative as well. And then maybe actually we had more items here. So we have more here. And then eventually this level gets compacted into level 2. And then the picture there is basically now, we only store again the representatives. But there are these other items that, that were there, etc. Right? So, so basically the thing is, all these items that aren't stored, they're, it's because they're representative somewhere. Okay. Some of them might be representatives on the other side. Okay. So there are a bunch of representatives in here. Right. So this is basically the source of the error, because these things that are being kind of merged in, we don't actually know how they compare with X, right? They might be less than X, or they might actually be bigger than X, but they got merged on the wrong side, so we're confused. Okay. Or, if you want to think about this happening and, if you want to follow the compactions in real time, just in the analysis, imagine all these black dots are the stream. And then whenever there are some compactions, some of the thing, there's some mergings happening into these boxes, and there's some error that could be introduced because someone who was on the left side of X might have gotten merged onto the right side, or someone who was on the right side might have gotten merged into someone on the left side, and that introduces error. Does that make sense? So to answer a query, rank of X will return the sum over J goes from, let's say, 0 to log of n over k minus 1. This is the number of compactors we have. The sum over y in compactor J such that y is less than or equal to x of 2 to the j. Right? Because this item y represents 2 to the j items, right? It's a representative of 2 to the j items. And we're hoping that these 2 to the j items are all correctly less than or equal to x, but of course we might have had some error because people got moved from the other side or moved out. So yeah, so the compactions, I mean, we reduce memory, but naturally, as you can see, there's error that's introduced from compaction. So this is the same thing as basically, yeah. So that's what we're returning from. That's what we're returning from rank. So now, what's the error? Well, each compaction at level J, when I say at level J, basically what I mean is, into level J. Into level J introduces an error of at most 2 to the j minus 1. Right. Okay. Any questions about this? Right, because again, you have a compaction. So let's just look at, compacting into level 1. So these are the items I'm compacting. Here's my query X. And when I compact, these two, I sort before I compact. So, these two get merged, and then this is the representative. These two get merged, and this is representative. And then these two get merged, and then, this is the representative. So actually, in this case, there's no error that's introduced. There were 4 elements that were smaller than me, and they each counted as 1 element. Now there are 2 elements, 2 meta elements that are smaller than me, and they each count as 2 elements. So I'll still think that there are 4 smaller than me. I guess the bad case is, what if instead of x being there, you actually had x being here? Kind of in between 2 elements that got 2 elements that got merged together. Now, in level 1, I'm only going to see 1 merged element less than me, right? The representative from the second merged element is actually bigger than me, so I'm not going to count him, right? So there's basically this kind of 1 merge that's happening at the boundary that includes x, which is going to create error, right? So here I'm going to be off by 1. I'm going to miss this 1 element that's less than me. But, at higher levels, that 1 element that I'm missing actually has weight 2 to the j, right? At level j, it has weight 2 to the j. So it's going to introduce this error of 2 to the j minus 1. Okay. So every compaction that happens introduces an error of either 0 or 2 to the j minus 1. So it's at most 2 to the j minus 1.
I have a question about these compactions.
Yeah.
So it seems kind of like how there's kind of bit increasing behavior where at certain points, it kind of could send all the compactions to the end. If the first 5 of your are half full and you fill up the first one.
Yeah, it will chain together. That's right.
Yeah. And then I'm wondering is is after this like big chain happens, like if you query like right before versus like right after, is it a lot more coarse right after this big chain, and have like maybe like with the error bound it's the same, but like what have like just like worse rank approximation like after a big chain versus like right before like this like big chaining happens?
Oh, you're saying is the quality of your approximation better at some times than others? Is that your
Yeah,
question?
yeah. With this like specifically with this like big chains. Like if I like half full my first 5
Yeah.
versus it all kind of gets propagated to my 6th compactor.
Yeah. So I mean, okay. So our error bound is going to be precisely the following
Yeah.
thing,
Mm-hmm.
which is going to be the error. All I can say is that the error is at most basically the sum over j goes from 0 to like, let's say this is the highest level compactor of the number of compactions into level j times 2 to the j minus 1, right? So that's all I can say. Now, I mean, I guess looking at the state of the data structure and knowing which things are empty and which are half full, I can infer, I guess, well, I mean, I can infer then what n is, right? How many things there have been, how many insertions there have been, and I basically know how many, that implies the number of compactions at every level, right?
Mm-hmm. Okay.
Yeah.
Yeah.
So,
So
for
then,
example, if the very last level compactor that has anything in it at all is level L, then and it's half full, I know that there was exactly one compaction at level L minus 1, right? And then
two.
based on whether
Okay.
level L minus 1 is currently empty or half full, that can also tell me how many compactions there were therefore at level L minus 2, etc. But I mean, I'm going to give a bound on this right now, which is equivalent to that. So maybe let me just write this down.
Mm-hmm. Okay.
Does everyone understand now why I'm writing this? Does it make sense? Okay. So what's a bound on the number of compactions into level J? Well, so think about it like this. Whenever there's a compaction at level J, that means that it got filled up to K items, okay? And okay, so actually let me state this. How many compactions could there ever be from level 0 into level 1? Okay. Well, every time you compact, you throw out K items, right? Half of them get promoted to the next level, but you had K items and now you get rid of all, you flush them all out. You flush out K items. How many items are in the stream? N, right? So there are N items, you're flushing out K at a time. How many compactions are there out of level 0 into level 1? At most, N over K, right? Similarly, if you're at level J and if you're at level J minus 1 and you're compacting into level J, okay, well, whenever you flush items out of level J minus 1, there are K of these items, but each one of those items actually represents 2 to the J minus 1 items, right? So, the number of items that can ever appear, right? The number of items ever living in compactor J minus 1, is at most N over 2 to the J minus 1, right? Because each item that lives there actually represents 2 to the J minus 1 items. And there are only N items total. So this implies that the number of compactions from level J minus 1 into level J is at most N over 2 to the J minus 1 over K. So there's a K in the denominator. Okay. So all that means basically is if this is this, that's this thing right here. It's N over 2 to the J minus 1 times K. So the 2 to the J minus 1s just basically cancel. And then this is at most nh over k, and h is log n over k. So n log n over k, right? And I want this to be at most epsilon n. So if you solve that, you want n over k log of n over k to be less than or equal to epsilon n, you'll get that k is then, the solution to this is based up to a constant factor, 1 over epsilon log of epsilon n. And that gives you exactly the bound that I promised you.
Yeah, seeing this helps.
Okay. Any other questions? Okay. So now let me talk about randomized algorithms. Oh, and I did mention, of course, keep in mind, we do know what the optimal bound is for comparison-based algorithms, and that's this one, which I will not do today. So basically what I just showed you now is within a log factor of this. Instead of log, it's log squared, but you can actually achieve log. Okay. Okay, so now let's do randomized. And there's the KLL sketch. Which they named after themselves, Karnin, Lang, and Liberty. This is in 2016. Okay. And what it achieves is the memory is O of 1 over epsilon log 1 over delta. Okay, so before I show you that algorithm, I'll show you, it's basically builds off an idea from Manku, Rajagopalan, and Lindsay. So I showed you their deterministic algorithm from '98. Then they also had an idea for a randomized algorithm. Okay. Instead of promoting every, let's say, odd index element, during compaction, you could also promote every even indexed element, right? You would basically have the same kind of error guarantee. So what they do is they randomly choose. Whenever they do a compaction, they sort, and then they randomly, uniformly at random, either promote the odd indexed elements in the sort or the even indexed elements in the sort. Randomly promote either the odd or even indexed elements. Okay. Okay, so how do you analyze that? Okay. And basically the idea here is as follows. So remember this picture. Where do I want to put X? Let's say this is my query X. And then I do a compaction. Okay. Now, when I do this compaction and I query the rank of X, I'm either going to say 2 or 4, right? If I choose to promote the, I don't know if let's do zero-based indexing. So the first element has index 0, which is even. So if I choose to promote the even index people, then I'm going to think that the rank of X is 4. However, if I choose to promote the odd index people, then I'm going to think that the rank of X is 2, right? So I will be off by 1, but I'll either overestimate by 1 or I'll underestimate by 1, randomly, right? And the point is, before I was always kind of estimating in the wrong direction, and all these errors were just, additively accumulating. Okay. And now they're accumulating, but with random signs as coefficients. So that's that. And so, ideally then the sum, when you put the random signs on them of these errors, will be smaller because some of these errors will cancel out because they have random signs. So now the error basically is equal to the sum. J goes from 0 to H, and the sum from, let's call it, R goes from 1 to MJ, MR. MR is the number of compactions at level R of 2 to the J minus 1 times sigma JR, where, and let me actually, be a little more precise in this. Eta JR is sigma JR. Okay, where eta JR is in 0 or 1. Remember, we saw, for example, if X was not in between those two elements, what was right next to them, we would have no error, right? So if X were here instead, we would not have error. No matter whether we promoted the odds or evens, we would correctly say that there are 4 elements less than X. So sometimes there's no error. So eta is basically zeroing out error that we might have had in that compaction because there was no error. But if we do have error, the error will either be plus 2 to the J minus 1 or minus 2 to the J minus 1. Okay. And then there, that's what sigma is. Sigma is a uniform random variable that's either -1 or +1. Okay. So let's call this error, the error is E. So E is basically this random variable that involves some etas and some sigmas. The etas, as we're going to see, don't matter a whole lot. In fact, if all the etas were 1, you could imagine that's the worst case because all of them are contributing to error. But basically, no matter what the etas are, we're gonna show that the error is bounded. Okay. Okay, good. So I would like to say would like that the probability that this error is bigger than epsilon n should be at most, delta, right? That's what I want. And the question is, what can I tune here? The only thing I can tune is K. Remember the size of the compactor. So the question is, what setting of K will give me that? So any questions before we do that analysis and see what K we can get away with? Okay. So we'll need a probabilistic inequality. And I won't prove it in class, but I will include it in the lecture notes so you can read about it if you'd like to. It's called Khinchin's inequality. Okay. And what this says is, let's say that sigma 1 up to sigma t are IID plus minus 1 uniform, okay, random variables. And let's say that we have numbers x1 up to xt that are real numbers. Then it says that for all lambda bigger than 0, the probability that the sum of sigma I xi. So what is the expectation of this random variable? Sum of sigma I xi? It's 0, right? Just by linearity of expectation, each sigma I is a plus minus 1. It has expectation 0. So we'd like to say that it's unlikely that this random variable is large because we expect it to be 0. So the probability that it's bigger than lambda in magnitude is at most 2e to the minus lambda squared over 2 times the L2 norm of x squared. Okay. So just a comment. Okay. If sigma 1 up to sigma t had been independent Gaussians, G1 up to GT, then sum of GIXI is a Gaussian with mean 0 and variance equal to L2 norm x squared, right? So I don't know if people have seen this, but if you take independent Gaussians and add them, what you get back is a Gaussian whose variance is the sum of the variances of the Gaussians that you added, right? And so GI has variance 1. GI times some fixed constant c has variance c squared. So GI times xi has variance xi squared. So when you sum GI your variance becomes the sum of the xi squareds. Okay? So, if this had been Gaussians instead of plus minus 1s, then that sum would just be a Gaussian. What's the probability that a Gaussian with variance L2 norm of x squared is bigger than lambda? It's exactly that. It's exactly what I wrote here. This is the tail bound for a Gaussian. Okay. So what this Khinchin's inequality is saying is plus minus 1 random variables have the same kind of tail behavior, or their tail behavior is bounded by that of a Gaussian. This is also known as, so this is saying that, what's called sub-Gaussian. That sum of sigma I xi is what's called sub-Gaussian. It decays at least as fast as a Gaussian does. And in fact, the proof that I'm going to put in the notes is a very simple proof that it's going to directly relate the answer to Gaussians. Yeah. And then there you can just look up what is the tailbound for a Gaussian, or you can try to prove it. I'm not going to prove it in class. So why is this relevant? Because in our case, remember, for us, we have this error, which looks like the sum, there was a double sum. Sum over j goes from 0 to h. And then the sum goes from 1 to mj of sigma jr times something. The something was eta jr times 2 to the j minus 1, right? This, of course, is my xjr, right? So I exactly have the setup of Khinchin. I have a sum of independent plus minus 1 random variables times other stuff. So now what's my L2 norm of x squared? Okay. This is equal to, well, it's at most, this is why I was saying it doesn't really matter what the etas are. If all the etas were 1, the etas are either 0 or 1. So the L2 norm squared is upper bounded by the case that all the etas are 1. So this is at most the sum j goes from 0 to h of 2 to the 2j minus 1 times mj. And remember what we bounded mj before. Mj was at most, this is the number of compactions there are at level j. So this is at most n over k times 2 to the j minus 1. That's what we saw before from the MRL analysis. And then now we get a little bit of cancellation, right? This cancels that. And then n over k just gets pulled out of the sum. So this whole thing is at most n over k times the sum 2 to the j minus 1 up to h. Actually, this should be j goes from 1 to h because we said we're compacting into level j. We never compact into level 0, which is less than n over k times 2 to the h. And h is log n over k. So this is basically n squared over k squared. Right? So L2 norm squared for us is n squared over k squared. So let me actually try to, just so that you can refer back to the inequality we have here. This is the inequality we're using. Let's use it. I'll just do it right here. This is this thing, okay. So the probability that our error is bigger than what we want the bound to be, epsilon times n, is at most 2e to the minus epsilon squared n squared times k squared over n squared, and there's an over 2 here, right? Because we get to divide by the L2 norm of x squared. So we get to divide by n squared over k squared. So n squared cancels. And we basically just have this k squared. So this implies we can set k to be something like 1 over epsilon times the square root of log 1 over delta. Right? We want failure probability delta at the end of the day. So that's it. So we get here, so this, we get k to be 1 over epsilon root log 1 over delta. The space is k times log of n over k, which for us then becomes something like O of 1 over epsilon square root log 1 over delta times times log of epsilon n over root log over delta. Okay, so that's already something, right? Remember that MRL was log squared n. If you think of delta as being, let's say, a constant, like 1 over 100, then root log 1 over delta is a constant. So already we've improved log squared of epsilon n to log of epsilon n. Okay, which of course is, Greenwald can do that deterministically, so that's not great. So how can we do even better? So one of the ways to do even better, so improvements. So what MRL realized was one way you can improve this is via sampling. So can combine with sampling. And the idea there is if you keep a random sample of O of 1 over epsilon squared log of 1 over epsilon delta elements, let's call this n prime from the stream. Okay. Then you can show via like the Chernoff-Hufting bound that if you then just answer, approximate rank and quantiles are the same. Rank is like, what's the rth smallest element? Quantiles is like, what's the alpha nth smallest element, where alpha is a fraction between 0 and 1? What's at the 25th percentile? What's at the 50th percentile, right? So those are equivalent just by, you can multiply alpha by n, that would give you the corresponding rank. Or you could divide the rank by n, that would give you the corresponding percentile or quantile that you want. Okay. And if just by the Chernoff-Hufting bound, basically what you can show is that if you keep a random sample of this size, then you'll give that alone will give you an approximate quantile data structure. Basically, when someone asks you what's the median, you just return the median from the sample. When someone asks you what's at the 25th percentile, you just return what's at the 25th percentile from the sample. And you can show that this will actually do that for you, okay? So now what you've done is you've reduced, so let's say you know n in advance, okay? So what you do is each item you see in the stream, you actually just remember it with probability n prime over n, otherwise you get rid of it, okay? And then what you do is you feed this sample into the data structure I just showed you, right? And the point is that n is now smaller, n is now n prime, so this n gets smaller, okay? In particular, that n is something like rough poly 1 over epsilon log 1 over delta, right? So this implies a space bound of something like 1 over epsilon root log 1 over delta times log of epsilon n prime over root log 1 over delta, which is the same thing as 1 over epsilon root log 1 over delta times log of, it should be something like, I think log 1 over epsilon, is that right? Yeah, basically log of 1 over epsilon plus log 1 over delta, something like that maybe. Or another thing you could do is you could then feed the sample into, actually a better thing you could do is just feed the sample into a deterministic data structure. Like feed the sample into Greenwald-Kana. If you feed it into Greenwald-Kana, that will actually even get rid of the square root log 1 over delta. Okay. But you can do better, and that's the KLL sketch. So what does the KLL sketch do? Okay. It uses, first of all, so the first idea that they had was to use geometrically changing compactor sizes. So your first few compactors are actually going to be quite small. They're going to have size 2. And then the last one is going to have size k. And then the one before it is going to have size basically 2/3 k. And the one before it is going to have size 2/3 squared k, etc. Okay. At some point, 2/3 to some power k is going to be less than 1. So what you do, you kind of bottom it out at 2. So you never let the compactor sizes get less than 2. And then you do exactly the way that we were doing things before. You insert into the bottom compactor. When it becomes full, you promote half the items, either randomly the odd or the even, into the next compactor, etc. And then everyone in compactor J again has weight 2 to the J. That doesn't change. All that changes is that the compactors no longer have uniform weight. Okay. And then a lemma, I don't have time. I'll include it in the notes, but I won't show it here, is that first of all, you still have that kind of, okay, I guess you still have that MJ. The number of compactions at level J is at most, well, okay, so, let me not, actually, just give me a second. Yeah, so actually, yeah, I'll just let me prove this in the notes. Is that the x equals to norm squared that you get from this, right? Because now, you know, the sum isn't exactly the same because, you know, you have to again correctly bound the number of compactions that happen at level j, and then you'll get a sum that looks similar to basically this sum, right? You'll get a sum again that looks similar to this sum. Okay, but you need to bound mj appropriately and also bound how big h gets appropriately. But the punchline is that if you do that, you can get this thing to be at most still O of n squared over k squared. The beauty of that is you're still getting the same exponents in that tail bound, so you can still set k to be the same as before. So what's the benefit? The benefit, though, is that the compactors are not all the same size. They're geometrically decreasing, right? So instead of paying a log n factor times that in your space, you're only paying an additive log n. And the reason it's additive, you know, each one of these compactors does have size at least 1. So you do have to pay an additive log of n over k because they're, you know, rough O of log n over k compactors. Each one has size at least 1. So this implies space that's O of 1 over epsilon square root of log 1 over delta, basically plus log n over k, which would be something like log of epsilon n over root log 1 over delta. So the benefit that is that this used to be a times, but now it's a plus. And then the last finishing touch to get the space even better is two things. So the final touches, there are two final touches. What are these two final touches? One, you have all these compactors in the beginning that just have size 2. So what is it really doing? So, you know, some items, so let's say that there are L of them that have size exactly 2. You can think of this as like kind of one big black box where, you know, 2 to the L, so, you know, 2 items come in here, the first one, then when this one gets full, that represents basically 4 items, etc. So when the last one gets full, I'm sorry. You know, this represents like 2 to the L items, and then 1 gets spit out. 1 item gets spit out during a compaction, and this represents 2 to the L plus 1 items. So you can think that kind of every 2 to the L plus 1 items that comes in here to the left of this big circle, this big oval, 1 item gets spit out. And which item is it? Well, since you're always promoting a randomly odd or even, here odd and even just means the first element or the second element because there are only 2 elements. The item that gets spit out at the end is actually a uniformly random element amongst those 2 to the L plus 1 items. So what they say is rather than spend L units of memory or 2L units of memory with these L compactors of size 2, we can just implement this entire oval as a sampler that, you know, samples every 1 over 2, you know, out of every 2 to the L plus 1 adjacent items in the stream, it samples 1 of them uniformly at random. So implement as a sampler in just O of n memory. So that's the first optimization they do. And the second optimization they do is, remember our error is going to look like this double sum. J goes from 1 to H. R goes from 1 to MJ of this sigma JR times some coefficient. And this coefficient was 2 to the J minus 1 times eta JR. So what they do is they actually separate this double sum into 2 parts. They say that this is the sum of small j. J goes from 1 to H minus S, so don't go to the end, go to F of sum over r minus 1 mj of all that stuff, plus the sum j goes from h minus s plus 1 to h of the sum r goes from 1 to mj of sigma jr eta jr to the j minus 1. So they break the sum into two parts. And then they say, let's bound the error from this part using Kinchin, which you've already seen. And for this, we're going to use a trivial bound. What's the trivial bound? The trivial bound is just bound all of the random signs by 1. So the trivial bound is that this is at most the sum j goes from h minus s plus 1 to h of mj times 2 to the j minus 1. We don't take advantage of the fact that there could be cancellations from the plus minus 1. Okay. And if you do this and pick the right value of s for the calculation, s being something like log 1 over delta, and you also make the last k compactors, or the last, s compactors, have size exactly equal to k. Don't make them geometrically to k. Make them all have the same size. Then you can show that, in fact, you can get away with k being even smaller. And that will give you a bound, if you do this correctly, of 1 over epsilon times log 1 over delta squared. Okay, so I know I'm basically out of time, but let me just draw the picture. The picture basically looks like this. The first few levels all get implemented just as a sampler in constant memory. Then this gets fed into a sequence of compactors that are geometrically increasing in size. And then that gets fed into compactors that all have the same size k. There are s of these. All of these s have the same size k. These are geometrically decreasing in size. These are geometrically decreasing. So there are basically 3 components you can think. There's the sampler, there's the part that's geometrically increasing in size, and then the final s that all have the same size. That's the data structure. And you can show that this achieves space 1 over epsilon times log 1 over delta squared if you analyze this appropriately, where s is log 1 over delta. And to get the actual optimal bound, what you do is you actually cross this part out, and you just put an optimal deterministic algorithm here, which is, for example, the Greenwald-Connaught algorithm from 2001. So this arrow actually feeds into the GK algorithm. And if you do that, that gives you space log 1 over delta. Okay. So that's it. I know we're slightly over time. Any final questions before we take a break until Monday? I know I didn't give all the details for the more sophisticated stuff, but at least you did get to see all the analysis details for some of the simpler variants that still get decent space bounds.
Wait, sorry, do we not have class Wednesday?
It is Wednesday.
Today is Wednesday.
Remember, Monday was Labor Day.
Oh, God.
No problem. Okay, so I will see you all Monday. Okay.
Thanks.